Okay, so far we've focused on the probability of different events occurring. Okay, and these are sets of outcomes. But sometimes, rather than considering sets of outcomes, we want to think about the value associated with different outcomes. Okay, and this is where the idea of a random variable comes in. Okay, so the definition of a random variable is a function. So a random variable is a function such as capital X that goes from our sample space over to a set of numbers, to the real numbers. Okay. Now, we don't have to have the real numbers here. It could be another set, but for now, let's just stick with the real numbers. Also, another thing to add is often people use capital letters for random variables. You don't have to, but ordinarily people have things like capital X, capital Y, capital Z, things like this to indicate that you're working with a random variable. Okay, that's a convention, a bit like using boldface for vectors as well. Okay, so random variable is a function. Okay, and it gives a number. So that gives a value or a number for every outcome. Okay. So a simple example might be that we throw two coins and consider the random variable. Throw two dice and consider the random variable that consists of the sum, okay, of the two dice throws. So you could have, so here we would have a sample space that consists of all the dice throws that we can have. So 1 and a 1 and a 1 and a 2. We wrote this out earlier, going all the way up to 6 and 6. Okay, and then x would then be the function that goes from our sample space, okay, to, well, numbers between 2 and 12. Okay, so x of the outcome little xy, or let's say this is a different letter, d1 and d2, where d1 is the number from the first dice and d2 is the number from the second dice, is just equal to d1 plus d2. Okay, right. So one thing to add, to mention, is that random variables they can be discrete or they can be continuous. Okay, and one thing to say is sometimes I'll write RVs or RVs, okay, R dot V, to make things a bit shorter. Okay, so random variables can be discrete, okay, meaning that although we go from our set of outcomes to the real numbers, we might only take a finite or countable number of outcomes that can occur here. Okay, so they can be discrete. By this I mean values like 0, 1, 2, 3, or just in any countable subset of the reals, or they can be continuous. and that can mean that they can have values across a range of values in R. The real numbers. Okay, so you can consider things like height or time as things that could be random. Okay, so length and distances, okay, which might be random, like how far do you throw, I don't know, a rock or something like this, okay? There, the length that the rock goes is a random, potentially random amount, but it's on a continuous range, okay? There are things in between discrete and continuous as well. Okay, now for now, let's focus on discrete random variables, okay? So we'll discuss that next. So discrete probability distributions is what we're going to chat about next. Okay, so the probability distribution of a discrete random variable x is given by p of x, which is just the probability that x equals x for each x which belongs to the range of x. I'm going to denote the range like this for now. Okay, so here this is just the range, sets of values that this random variable could take. Okay. Right, and just like with so this defines the probability distribution of this random variable. Okay, it's also sometimes called the probability mass function. Okay, so when we say probability distribution of a random variable, we mean any random variable, discrete, continuous, or otherwise. And when we're specifically talking about discrete random variables, we tend to use this notion of probability mass function. Okay, and the properties that this satisfies are just the same as before. That we need the probabilities, okay, of each event, of each outcome or each value of the random variable to be positive, and we need them to sum. Okay, up to 1. Okay, and then that's it. All right. Okay, and one further thing I'd like to add is, well, let's consider the setting where we have more than one random variable. Okay, so suppose we have two random variables. Okay, so use shorthand RV meaning random variables, x and y. And notice they should both be on the same probability space. So x here is a function from our sample space to some range of values, which is some subset of the real numbers, and y is going to be some function from our sample space to some appropriate set y, some discrete set y. Okay, now we can define the joint probability distribution of x and y. Okay, so the joint probability distribution of x and y is given by, well, you could write it as p x of y, and it's the probability that x equals x and y equals y. So the probability that x is equal to x and y is equal to y. Okay, so really what I'm saying is we're working out the probability of this event, and that's the event that x equals x and y equals y. Okay, one thing to say that often in probability, and I think in set theory as well, when we add this comma, really what we're meaning is and. So really this means the probability that x equals x and y equals y. Okay, but often it doesn't make sense to make this quite so explicit as saying like sort of A intersection B. It looks a bit ugly to do all these curly brackets and then this and symbol, and so sometimes this is just shortened a bit with this comma notation here. Okay, so that's the way you can specify the joint probability distribution of x and y, and we do this for x belonging to the range of x and y belonging to its range y. Okay, now one thing we can add to this, and notice we could extend this, we could have y, x, y and z, or any number of random variables that we like really, and keep this definition going. Okay, notice once again we're going to have the same properties as before, that all of these numbers are going to be positive, and if we sum over x and y, okay, so what I mean is we sum over x, and then we sum over y belongs to its set pxy, and this is going to sum to 1. Okay, but anyway, that's not so important given the previous definition that we've given. Now we can talk about random variables being independent as well. We say that x and y are independent random variables if we have that the probability of x equals x and y equals y is just equal to the product of those two probabilities. Okay, so if we thought of it this way, we could think that the pxy is just equal to the probability mass function for x multiplied by the probability mass function for y. Okay, so the same ideas of multiplying continues, and we need this property to hold for all the x's in the range of x and all the y's in the range of y. Okay, so that's a few definitions to work with. Now we're going to start to talk about what we expect to happen with these random variables. So remember, for example, when we summed up the number of heads that come from, say, 100 independent throws of coins, okay, I wanted to understand what the expected value of that outcome was. Okay,